All right, this is really going to be chapter 22. We are going to change gears just a little bit. It's going to be starting with, it's the same thing we've always done with significance tests and confidence intervals. But now instead of just with one sample, we're going to be dealing with two different samples. Okay? Don't write that down, that formula. If you have, it's fine. It's the z-score formula. There's a much more condensed version. Here they've got it factored apart, and that's not quite necessary. But we're going to talk about confidence intervals, standard error, significance test, and what it means to pool our proportions. And when would we pool and when would we not pool. P-hat, if I'm looking at two different samples, if I'm looking at p-hat in terms of the unified p-hat, you would take the successes in both samples divided by the observations of both samples combined. So really, if I had two different sample sizes of 200, then my p-hat would be out of 400. And so that's effectively what we do when we pool something, is we put all of our information together. And so you've got these different values like that. Questions about anything before we get started?
Did you say, can we write the p-hat formula but not the
Sure,
one?
you can write the p-hat formula. Okay. So here's an example. In a treatment group, you have 2,051 middle-aged men and 56 had heart attacks. In the control group, we had a placebo. 84 of the 2,030 men in that group had heart attacks. The idea is that the treatment reduces the heart attacks. We want to perform an appropriate test for this particular example. So let's do the calculator part first. Go ahead, and I want you to go to your calculator and go to Stat. Go over to Calculate, and I want you to go down to mine is number 6, 2 Prop Z test. Okay, go to tests. It's going to ask you for a number of things.
Are we going to have the treatment group 1 and the placebos 2?
Control group, we'll do it in the order that they gave it to us.
Okay.
Treatment group is going to be the first group. So in X1 and in N1, let's input our treatment. So we had 56 successes out of 2,051 sample size. Number 2, we had 84 successes out of 2030. Successes here is kind of morbid, but the term success and failure is left over from when we used to do probability with gambling exercises. Okay? So just think of the success as an outcome that you're looking to find and things like that. Right. And so the idea is the treatment reduces heart attacks. So here's where you're going to have to be really careful about writing your alternative. So just for a second, let's talk about what would your HO be?
It'd be
Let's say that P1 is the treatment and P2 is the placebo. So what would my null hypothesis be here?
P1 minus P2.
P1 minus P2 would be what?
Is it 0?
Would be 0. Somebody read their chapter.
I don't know.
Why?
We don't.
Why would it be 0? What was the idea? Null hypothesis is the absence of the effect.
Yeah.
So the idea is that it reduces. So if there is no difference in the two, then the drug doesn't work. So we're going to assume that there is no difference. That the proportion of men that have heart attacks in the first group is the same as it is in the second group. So when I subtract those two numbers, I should get 0. What would your alternative be?
Greater than 0. Not equal. Greater. P1 is
Be careful. which one is supposed to be more?
Placebo.
P2 should be 0, right?
It'd be less than.
I mean, it should be more. The placebo should have more heart attacks. So when I say P1 minus P2, what should that value be? Positive or negative?
Negative.
So we were going to say less than 0. If you had turned it around and said the other way around, then your alternative would have been backwards. The way that you set this up and the way that you put it in the calculator better match up. Now, there's an easy way to determine. If you get a really, really high number here, then it's not going to be. So our alternative is going to be the less than alternative. Right? So go ahead and hit calculate.
Wait.
What do we have?
P
And-
equals 0.0067.
Oh, I thought you could see. That's kind of awesome.
So now, it tells you a lot of things. If you will, just scroll down once you've created that or that test.
It's handy.
You have your P1 is less than P2 alternative, which says the people that have the actual medication should have less heart attacks than the proportion of the placebo. Makes perfect sense. The Z-score,
Wait, say
there it
that
is.
one more time.
My alternative is P1 is less than P2
And how did you know that again?
because that's what I chose. I chose less than. That means, let me go back to my picture. Look at this. Alternative. If you take that, let's go ahead and put P2 on the other side, right? And so that would be P1 is less than P2. This is also a way I could write this. I could also say P1 is equal to P2. That's also a way I could write that. Both methods are accurate and accepted. Okay? It's more common to write the difference of them because that's what we're trying to find. We want to know, is there a difference between these two groups? So we kind of write our alternative that way. Plus, it helps us to think about less than, greater than. But if you like the other way, it's fine. You can write it. If you like the,
Were
ma'am.
you talking about the X's when you were
Mhm.
talking about the P's?
The proportion, I didn't actually find the proportion of people that had heart attacks in the treatment group and the proportion of people in the placebo group, but that's the proportion we're talking about. We would expect the people that did not get the medication to have more heart attacks. That would be the placebo group. And so in this case, P2 should be a bigger number,
Which it is.
in which this case, that's what my alternative says. Okay?
Which it is.
Correct, right. Yeah, it's a lot more. And so if you go back to your calculator, scroll down. It gives you P hat 1, P hat 2. It gives you P hat in general. That's the pooled number. Pooled number is combined as one big sample. Because theoretically, these people are just coming from the same population. Okay? It gives you the p-value by itself, which is 0.0067. So we would reject the null in this case. The fact that they are the same. And so we would conclude that the actual treatment is having effect and lowering the risk of heart attack. We have a lot of evidence to suggest that. And so you would make that statement.
Bad question.
Can you construct the 95% confidence interval for this? Here's something really interesting. Go directly to your 2 prop Z interval. Don't type anything in.
What'd you say go to?
Go directly to the 2 prop Z interval and look at your data.
That's already there.
It's already there. Your calculator has a memory for X, for N1, N2, X2. And so if you want 2 prop Z interval, go down and go ahead and create your 95% confidence interval. It's really nice that it's already there. And so you should get
Did you get a negative?
negative 0.025, comma, negative 0.0029. Now, can someone explain that to me?
You are 99. Or what was it, 95?
95% confident
With 99?
that
That the
between-
number of heart attacks falls between that and that?
Yeah, how do you do that with
Okay, here we go. This is an interval which has negative values. Remember, we're subtracting. We assumed that the difference of P1 minus P2. So if I said the people in the heart attack group, or in the medicine group, minus the people in the placebo group. So when I subtract, I should get a negative number. If the medicine group really is reducing that number. So the fact that 0 is not inside that interval is more evidence that the medication is reducing the proportion of heart attacks. If it had been positive, because I subtracted the P1 minus P2, then it would have been showing that the placebo group had a reduction in heart attacks, not the medication, which is crazy. If 0 is inside my interval, then that means 0 was a possible it was a possible difference. It means that I do not have enough evidence to say that there's a true difference between the two, because 0 could have been one of the differences. If 0 is in the interval, that means that 0 is a possible choice for your difference. If that's possible, it means it is possible that there is no difference in the groups. To correspond to my alternative, okay, because 0 is not inside this interval, we rejected the null. If I had failed to reject the null, then when I look at my interval, I would have seen 0 inside it.
I have a question.
Yes, ma'am.
I didn't get the same numbers you did.
Go to 2 prop Z interval. Check your 99%. It's 95%. Okay?
Okay, so couldn't you also, if you just had that, couldn't you also say that you could reject the null with the 5.05 alpha level because the confidence
Be careful.
alpha level equals 1?
Be careful. Shh. Don't fall into the trap of using a confidence interval to reject or fail to reject a null hypothesis. Confidence intervals don't have null hypotheses. It does support for or against it,
Right.
but you've got to go through that process of the significance test. It's evidence to go one way or the other, but don't think that it alone stands as a significance test.
And what is our script for the interpreting the confidence interval?
In this case, you'd see I'm 95% confident that the true difference in the proportion of the placebo group and the medical and the treatment group is between negative 0.025 and negative 0.0029. Because 0 is not in my interval, we believe that the treatment group really is having a reduction in heart attacks. I'm 95% confident that the true difference in the proportions is between blah, blah, blah. Okay, on to our assumptions and our conditions. So, I'm not going to spend a lot of time on this because you need to go ahead and read your chapter. You should have already read it because today was day 1. I expect the chapter read before you come to class. Independence, randomization, 10%, and success or failure goes the same, just like before. But for 10% and for success or failure, you must verify it for both groups. So it's like double.
Group 2.
Right. So group 1 here, group 2 here, and you check it for both groups. For independent groups assumption, this is the new one. What? Independent groups. For example, when we're looking at the two group before, you had the treatment group and the control group. I needed to know that not only was each individual person having a heart attack independent of one another, like if I had a heart attack, it's not going to make anything about you having a heart attack. But I also wanted to know that if this particular group, the control group, had no influence over the treatment group. If the independence group's assumption fails, then what turns out is we have a matched pairs design. It's like before and after. It's like a weight loss drug. Okay?
Does that mean that the groups are the same people?
Right. It means that my two separate samples have influence over one another. It means that I can't just match them up randomly. It means that this number must be matched with this particular number.
Are you saying that the question that we just did worked because they told you that they did choose two different groups of men?
Well, I need to make sure that the two groups are independent of each other.
Well, that would also.
And that's, for most of what we're going to do, that's going to be fine. Chapter 25, the entire chapter is about when the group, what happens when the group's assumption fails. And we have to take it a different route. It turns out we go from what looks like a 2-sample test to 1 sample.
Yeah, because that would be really hard to do there. That would mean a placebo also had the medication.
Right, and that won't. That did, for what most of what we're going to be talking about, it's not going to be anything that we have to worry about.
So, independent group's assumption just means that they're not in the same group.
It means that one group doesn't influence the other group. So here's my particular formulas for today. No. Standard error and your confidence interval formulas.
Same, we just add the extra.
It's exactly the same, except now instead of just one piece, I have to do it for both. For significance tests, did you notice that when you went to your significance test in the calculator, it didn't even ask you for HO? It didn't ask you for P0? Because P0 is always the same. We're going to assume that the groups are the same, that the difference in the groups is 0. The null hypothesis for a 2-sample scenario will never change. You won't have a number to compare to. What I really want to know today is this particular group like this group? Are they similar or are they different?
This kind of sounds like a stupid question, but in the standard error equation,
Do you add them before you take the square root, or do you
Yes.
take the square root?
You must, square root's last, the very last thing you do. So that confidence interval formula, it's the difference here, plus or minus z star times your standard error up top. But that standard error is the big formula up top. I just didn't want to write it twice. Your homework is going to be, I'm going to have to go ahead. I'm going to skip ahead. There it is. I'll go back. Write this down first. 1, 4, 7, 8, 10. Read chapter 22. And if you haven't read 20 and 21 yet, you should be embarrassed and ashamed.
4 times.
4 times is good. If you hadn't gotten it by now, there's just something not clicking.
No, you're like, well, go back and read your chapter. I'm like, I already did.